Welcome to an empirical study of refactorings and technical debt in machine learning systems. This is joint work with my PhD student, Yiming Tan, myself, Rafi Kachadorian, Mehdi Bangarzadeh, Ria Singh, Johnny Stewart, and Anita Raja. And I am from CUNY Hunter College and the Graduate Center. Machine learning systems, including deep learning systems, are pervasive in today's society. Not only do they consist of machine learning models, they also encompass complex subsystems that support the learning processes. And like other long-lived complex systems, they are prone to classic technical debt issues. Not only that, they exhibit specific technical debt in these systems that are specific to machine learning. As machine learning systems become more difficult and expensive to evolve over time, knowledge of the modifications required to them is of the utmost importance. Refactoring is known to be a widely accepted mechanism for reducing technical debt. Thus, understanding the kinds of refactorings performed in these systems yields insight into technical debt that they tackle. As far as we know, no previous studies quantify and qualify refactorings and technical debt in open source systems. Thus, we studied common refactorings in real-world open source machine learning systems to discover the kinds of refactorings made, their frequencies, the kinds of systems that they were made in, the types of technical debt they have addressed, whether the debt correspond to established ML-specific technical debt categories, or whether any new, possibly generalizable, ML-specific refactorings and technical debt categories could be derived. These results, we hope, can help improve and drive new ML-specific automated refactoring techniques, IDE code completions, and automated refactoring mining approaches. To summarize our contributions, we manually examined 327 patches across 26 open source machine learning projects. Then we built a rich hierarchical cross-cutting taxonomy of common generic and ML-specific refactorings. We marked whether they occurred in ML-related code, that is, code specific to ML-related tasks, such as classification, feature extraction, algorithmic parameters, and any ML-specific technical debt they addressed. At the end of the study, we introduced 14 and 7 new ML-specific refactorings and technical debt categories, respectively. Lastly, we proposed preliminary recommendations, best practices, and anti-patterns for long-lasting ML system evolution from our statistical results and analysis. As I mentioned, we studied 26 open source machine learning systems consisting of 4.2 million lines of source code overall, 175,000 Git commits, and 183 years of commit history. They vary widely both in domain, application size, and popularity. They exhibited non-trivial GitHub metrics and consisted of a mix of machine learning libraries, frameworks, and applications. At least one commit in the system must have mentioned the term refactoring and also involve a non-trivial portion of itself in the learning process. We favored Java systems, but that was not the only systems we studied, specifically since large-scale machine learning systems have at their core the machine learning models that are written in Python and C++, for example. Such subjects include Core NLP, Deep Learning for J, and Weka. To perform our study, we mined repositories for commit logs mentioning refactor, and then we randomly selected a subset of these to manually examine. We studied these code changes to determine the refactoring category, whether the refactoring took place in machine learning related code, and the ML-specific technical debt, if any, the refactoring addressed. To do this, we utilize reference bug reports to commit log messages. We also use some automated tools such as Refactoring Miner to isolate larger commits. To determine whether the code was in ML-related code, we looked for certain keywords such as cluster and train. As I mentioned, across our subjects, there's 175,000 commits. Of these, we found roughly 3,000 commits mentioned the word refactor. Of those, we randomly selected 327 to manually examine. We found that 285 of these were true refactorings. Some of the false positives occurred because, for example, they used the term refactoring out of context, or they were non-semantics preserving. Lastly, 165 of these commits we found appeared in ML-related code. We then devised a refactoring category hierarchy to 2 top levels, those related to and tangentially related to machine learning. Here is our diagram of the hierarchical discovered refactorings that you can find in the paper. This is the same diagram, just flattened into non-hierarchical way. You can see here that we have the 2 different branches, right? Generic and ML-specific. The ML-specific refactorings are ones that we've newly addressed. We also break them down into their overall counts and ones that are found in ML-related code. We can see here as a zoom in of the generic refactorings that roughly half of the generic refactorings took place in machine learning code. And here is a highlight of some of our findings. We found that performance improvements and reorganization, for example, introducing inheritance, were cross-cutting concerns that affected multiple categories, both specific and tangential to machine learning, and were among the most frequent. Duplicate code elimination was a major cross-cutting machine learning refactoring theme, combating debt in various ways. Inheritance introduction, which appeared under 6 categories, the most of any category, was a common and cross-cutting way to eliminate duplication and may be key in coping with the intrinsic variations that are found in machine learning algorithms. Despite being the smallest subsystem, machine learning related code was refactored the most. We also juxtapose technical debt with refactorings. On the left, we have the technical debt categories, and on the top, we have the refactorings. We broke these down into existing machine learning specific technical debt categories as one that and ones that we newly introduced. Here are some highlights of our findings for technical debt related findings. Configuration, duplicate code model, and plain old data type were the most technical debt categories. Duplicate code elimination was a major refactoring in ML specific technical debt, overwhelmingly related to configuration and implementing different yet related ML algorithms. So basically, those are the 2 main sources of the code duplication we found in machine learning code. Moreover, inheritance and other reorganization refactorings were commonly used in a variety of ML-specific debt, especially configuration. In other words, these were common mechanisms used to combat configuration debt. Here we have an example of a duplicate model code debt. Specifically, this is a pull-up policy or ML-specific refactoring that we derived. Here, multiple classes representing different clustering policies were presented. Each class previously implemented a common interface, but interfaces do not include functionality. As such, an abstract class is introduced that encapsulates common policy functionalities. And duplicate model code here is replaced with a polymorphic call to classify. In the paper, we have more details, such as more refactoring examples, common attributes of ML-specific technical debt categories, preliminary best practices, anti-patterns, and recommendations, as well as discussion and much more. In conclusion, we studied refactorings performed and the technical debt they alleviated in machine learning systems. We found refactorings both specific and tangential to machine learning. They occurred within and outside of machine learning related code. We constructed a hierarchical taxonomy of refactorings in machine learning systems. We found 14 and 7 new ML-specific refactorings and technical debt categories, respectively. We then preliminarily proposed recommendations, best practices, and anti-patterns put forth from the data that we found. In the future, we like to juxtapose findings with developer specialties and expertise. We'd also like to reuse the results to develop automated refactoring approaches. Another possibility is to integrate our results into automated refactoring detection techniques, such as refactoring minor. Lastly, we like to explore using refactorings to detect self-admitted technical debt. Thank you, and enjoy the rest of the conference. I'd like to take your questions at this time.
Hello again. Now we are in the second paper of this session. The second paper is called An Empirical Study of Refactorings and Technical Debt in Machine Learning Systems. And one of the authors is here to answer any questions. His name is Rafi Kachaturian. And now it's time for questions. So please, if you have any question, use the chat to ask the author. So the first question is from Sridhar. Sridhar is asking if you find some machine learning specific technical depths from a data perspective. In specific, what he means is if there are data specific machine learning refactoring such as noise in data and so on.
Yeah, thank you, Ignacio, and thank you, Sugar, for the question. So when we focus on the technical debt, we look basically for code smells. So by definition, really, of the classical understanding of technical debt is that these are emanating from either the source code level or something with a system architecture at the macro level. So we didn't really look to see if there were any kind of data related technical debts. That is an interesting idea that I don't think has been studied too in depth in the literature, and something that we can look into in the future. Certainly, we did focus on the classical technical debt of ML systems presented by Scully et al. And a lot of them deal with control structures, right? Experimental code paths and configuration debt. And I don't believe that we found any really related to the data itself in this study.
Okay, thank you. We have another question from Sira. Do you have any information on how the proportion of generic refactoring types found in machine learning-based projects compared to the proportions in non-machine learning projects?
Yeah, that's a great question. Thank you, Sierra. For this study, we just focused on ML systems, and we did not juxtapose that with other kinds of systems to see how those compare. But I think it would be a great idea for the future to take a look just at the generic refactorings and to see how that compares with other systems. My guess is probably they'll be somewhat similar because our corpus is a pretty diverse in its application, but certainly that would be some good future work. Thank you.
Okay, thank you. We have a question from the attendees. The next one is, do you have any insights into the interest paid due to these debts?
Yeah, thank you, Dinesh. That's another great question that we don't have an answer to at this moment. That certainly would be something to look at into the future. We did find a lot of bug reports and other things like pull requests and developer feedback, and a lot of them were lengthy regarding these technical debts that we found in refactoring. So it would be interesting to see if we can quantify that somehow, to see like how much time developers have spent dealing with these refactorings or technical debt issues. That's something, we have not done it yet. It sounds like great future work. Thank you again.
Okay, thank you. And I have several questions. The first one is about the need of specific tools for refactorings in machine learning. In what sense existing tools, because there are many tools now in the industry and in the academy for refactoring, and in what sense you need specific tools for a refactoring in the context of machine learning?
Yeah, thank you for the great question. So this was very much a formative study to set up, looking into what kind of tools that are needed. From our understanding, the majority of the focus has been more on API migration because ML and DL APIs have frequent versions, and that causes a lot of problems in ML systems. So we took a little bit of a broader view in this work to see if there's any ML-specific refactorings that are more general than API migration. So I would say probably the large majority of those existing tools have to do with API migration. And we hope to, as a formative study for this work, looking to developing these tools in the future for the refactorings that we've identified.
Okay, and my next question is related with the previous paper in the session. Is about your feeling about how you think that we can improve the adoption of machine learning in the industry, because maybe this poor adoption is because the tools that we have are not so developed enough to get a high adoption in the industry. I don't know, what do you think about it? Maybe a more powerful tools, including refactoring, are needed, or do you think that with the current state of the tools is enough?
Yeah, this is actually one of our findings, that we definitely need more tool support to support developers specifically in the ML area. Unfortunately, there's not a lot of that available. And part of the reason, I think, is because a lot of times these are developed in dynamic languages, and you'll find less tools for dynamic languages in general. But when we're looking at ML systems as a whole, a lot of these are heterogeneous systems in terms of the programming languages used, where only a small component really is the machine learning component, and you have a bunch of other components that are like feature extraction, configuration, a lot of things, data ingestion. There's a lot of supporting systems that can also benefit from ML specific refactoring. So I think definitely in the future we want to look, like I said, into trying to implement some of these refactorings that we found. And yeah, I think greater tool support could solve a lot of these problems.
Okay. And my other question is about your future work. What is your next steps in the next future to continue with this work? What are the next steps?
Yeah, thank you for the great question. Yeah, for certainly we would like to look into implementing some of the common refactorings we found. As I mentioned, this is very much a formative study. Another idea was from CIR, right, that we can also juxtapose this with non-ML systems to see if there's any differences in the generic sense. Another area of future work we found, we thought about was juxtaposing the findings with developer specialties and expertise to see what specialties or backgrounds developers come from and the kinds of technical debt errors they make or refactorings they produce. What are their specialties? What are their experience levels with ML? And lastly, we'd like also to integrate our findings with automated refactoring identification tools such as Refactoring Miner. So the focus on automatic refactoring identification has been very much on the classic refactorings that we've had for the past 2 decades or so. So it'd be interesting to see if we can incorporate some of these ML-specific refactorings into such tools.
Okay, we have another question from Ryan. He's asking about how do you expect these depths to change as machine learning software development continues to mature?
Yeah, that's a great question. Thank you, Yudesh. Well, I did mention the API migration, right, has been a huge problem with ML systems because the ML and DL worlds are changing so rapidly. It's definitely a big problem to keep up with those changes. So I think that's going to be kind of a focus going forward, that there could be some new technical debt associated with API migration. And there are also maybe things that are specific to ML or DL that could arise from that. But yeah, I honestly haven't thought too much of this question other than that. It would be interesting to see, as we have tools to help developers in ML and DL, and we see some of these debts decrease, what other debts would increase as a result, perhaps, or maybe some other areas as the area transitions into new kinds of learning algorithms and such. I certainly think it's also to see more configuration debt as these systems get more complicated in the future. Okay, thank you, Rafi. So if there are no more questions, I think it's time to say you goodbye. You have a very interesting work, and you can feel a clap from all the attendees. Thank you. Thank you very much, Rafi. And see you in the next session. All right, take care. Thank you. In the next paper.